In the fourth item, we have what is the longest item on the exam. It's a real true equilibrium problem. We're asked to find the force exerted by the two-force hydraulic cylinder CD on the pin C when theta is equal to 55 degrees. Right, and this is all going to start with a free body diagram of this part ABC. We've got the 10 kilonewton force applied in a vertical fashion. We've got an angular orientation here of the 55 degrees, which means that on the other side we're going to have an angle of 35 degrees. And we got the 0.8 and the 0.5 geometric distances there. And let's not forget here that we've got then two independent reaction components at B, and then we have the hydraulic force at the hydraulic cylinder that's going to go along the same line of action as the line from C to D. We don't know its angle, we just know that it's headed in that direction. There's your hydraulic cylinder force. That's the only way to keep this thing in equilibrium is, hey, the 10 wants to spin this part in a counterclockwise fashion about B. That means that C is going to have to be going in the opposite direction, as it's the only force that's there. So there's in effect tension in that system. Now, those angles are kind of confusing and difficult to me. So what I'm going to do to make my life just a little bit easier is not worry about it. Instead, think about breaking it into two different components, an x prime and a y prime, where y prime is directed along the line from B to C, and x prime is perpendicular to that. That'll make things a lot easier to work with initially. And so I'll have the component cy prime, which is going to go right through point B, and cx prime, which will be perpendicular to BC. That looks like, at least for the short work here, the equilibrium, that might work out to be a little bit easier here. So that's our second step, equilibrium. And if I sum moments about point B, let's take clockwise positive. I'll have 10. That's going opposite, so that's minus 10 times its moment arm. Well, it's not the full 0.8. It's just going to be that portion. It's down here. Oh, that's 0.8 times our cosine of 55. Right? That's our meters there. That's our kilonewtons there. Then I'll have plus our cx prime times its moment arm, which is the full 0.5. Set that equal to 0, and I find out that cx prime is going to be equal to 9.177 kilonewtons. Right? Now, I wish that was all I needed to know, but it's not. We need to figure out now what the angle is sitting in here or sitting in there. One of those two angles we got to play around with. And so that's where we got to go now look at geometry so we can get the whole set up. And so now let's draw the triangle BCD. There's B and D at 1.5 meters. And then we've got at 35 degrees BC, and then we got CD. Right, let's label what we know here. BC we know is at 0.5. We know that angle between BC and BD is 35 degrees. Right? We know that because if theta was 0, then BC would be hanging straight up. So the fact that this bracket is rotated clockwise 55 degrees, same as theta, means that this final angle there is 35. Right? And I look at that and say, I could play around with log cosines, I guess. Or, hey, you know something? Why don't we chop this triangle into two right triangles and start, because if I can start finding angles this way, interestingly. This little piece here would be 0.5 times cosine of 35 degrees, and that's going to be equal to 0.4096. Subtract that off of 1.5, and I get this other little segment. That's about 1.0904. Now the height of this little triangle right in there, that would be 0.5 times sine of 35 degrees, and that will equal 0.2868. That enables me to find this little angle down there, if that's the one I want to find. That will be equal to arctan of opposite over adjacent, so 0.2868 over 1.0904, and that's equal to 14.74 degrees. So, of course, I haven't really drawn this very well to scale, so that's kind of interesting. Maybe because I haven't done that incredibly well to scale, then how about we redraw this now that I know some things. And there's 35. This is probably still not to scale, but it's a little bit closer than it was before. Let's mark the angles we know. There's your 14.74. There's your 35 degrees. Add the two up, subtract from 180, and you'll get that this other one is 130.26 degrees. All right, well, now that's kind of interesting, because that's going to tell me that if I pull that out, that means C itself is going along right here, headed over. This is point C, right? And it's headed over to D. That's the force C. And if I go at 90 degrees to this, there was this X prime that I was talking about, and 130.26 minus 90 means that that little angle right there is 40.26 degrees, right? So since I know Cx prime, that means that C is equal to Cx prime over cosine of 40.26 degrees. And that means that when we substitute in our 9.177 over cosine of 40.26 degrees, I'm going to get 12.02 kilonewtons. And so my answer then for the force exerted by the two-force hydraulic cylinder CD on the pin C is going to be that this force C is a magnitude of 12.02 kilonewtons. It's pulling downwards to the right, and if I really care in terms of the angular orientation in the global coordinate system, it's at an angle of 14.74 degrees.